Okay, so in this presentation, I'm going to review the statistical test called one-way analysis of variance, and I'm going to demonstrate how to run ANOVAs using SPSS. So just a brief reminder of when we use an ANOVA test, a one-way ANOVA test. So essentially, it allows us to determine if one categorical independent variable that has 3 or more response options. I mean, you can do it also on a categorical independent variable with 2 response options, but you'd get basically the same result as a t-test. But regardless, ANOVA is particularly useful for 3 or more categorical independent variable, looking at whether or not there is a significant relationship with that variable and a continuous outcome. So when you run an ANOVA, how it works, you first have to look at the overall model fit and determine how well the groupings of independent variables account for the total variation in the outcome among all of the subjects or participants. So we do that through what's called an F-test or an ANOVA test, because the idea is that we are looking at whether or not there is a difference among the various means of these group categories, right? It doesn't, though, test or indicate which pairs of groups exhibit statistical differences. So then, if we find that the F-test is significant, we need to run what are called post hoc tests, one of which is called like the Tukey, highly significant difference test. So we apply those in situations where the F-test is significant. And so again, just as a reminder, ANOVAs are preferable to doing multiple t-tests because multiple t-tests are not independent of one another, which creates issues related to type 1 error. But the logic used in ANOVAs is very similar to the t-test. It's just a more rigorous analysis that helps us to avoid accidentally rejecting the null when it actually should not be the case. So the assumptions of ANOVA are basically the same as the t-test. So the first one is the assumption that we make for any inferential statistics, right? That our observations were randomly sampled from our population and are independent from one another. Then, though, we also assume our dependent variable is normally distributed and that there are equal variances within the population. But as with the t-test, when we have large data sets, large samples, we can relax both of these assumptions a bit. And then especially even if we have smaller samples, assumption 3 can be relaxed a bit if the sample sizes for the groups are similar in size. But if you have extreme outliers or errors in your data, you'll need to deal with them first. So that's why, again, going back to sort of exploratory data analysis, it's really important to have a good sense of the data you've collected and whether or not there's any sort of extreme issues you need to address before you start running your ANOVA. All right, and so finally, before we start getting into analyzing running ANOVAs in SPSS, I just want to underscore again the importance of aligning your research questions with your tests. And so in terms of ANOVA, here are some examples of some research questions we could ask around the topic of digitalization in higher education. So we could, with the ANOVA, look at digital literacy skills of students, which would be our outcome, our dependent variable, right? And whether or not those skills differ according to academic major. So as we know, academic major is a great example of a categorical variable with 3 or more categories. Many categories at Arizona State. I think we have like over 300 majors. But anyways, that could be a really good question to ask and address with one-way ANOVA. Another one, so student satisfaction with digital learning platforms, so that would be our outcome, right? Does that differ by class year? So first year, second year, third year, whatever, fourth year students, are they differently satisfied? Is there maybe an influence of class year on student satisfaction? Maybe the more experienced students have learning with digital platforms, they're more satisfied, or maybe it's the inverse, right? Maybe students get tired out of using digital platforms and they just want to be in front of a real person at some point in time as they're sort of approaching the end of their academic careers. Who knows? So that's a question, though, we could answer with ANOVA. We could also look at academic staff data sets. So maybe academic staff, we have a data set with how often they're using digital teaching methods in their classroom. And we could look at whether or not the use of teaching methods, the frequency, how often digital teaching methods are used, which would be our outcome, right? Does that vary according to the academic staff member's rank? So this is a question, a type of question, a type of analysis I do a lot in my research, because I look at academic staff careers, and a really important consideration is whether or not academic staff's pedagogical practices differ according to their rank. So good research question there to answer with a one-way ANOVA. Finally, we could maybe ask whether or not at a university level we can use ANOVA to sort of study more macro level trends across maybe a system, across the Ethiopian higher education system. So we could look at how many digital support staff are employed by every university, right? So to help out faculty and teachers in terms of developing and maintaining online or digital teaching and learning materials. So maybe we have a data set that has every university in Ethiopia, public university listed, and then the number of digital support staff that each one employs. And we could look at, maybe with a one-way ANOVA, whether or not there's a difference according to university type. So Ethiopia now has this differentiation strategy where the Ministry of Education has designated some universities as research, some as applied sciences, and some as comprehensive. So we could look at, with a one-way ANOVA, whether or not university type is associated with the investment in supporting and deploying digitalization at those different contexts. Okay, now I'm going to demonstrate how to run a one-way ANOVA using our CUIN dataset. So let's see here. Again, ideally, an ANOVA, a one-way ANOVA, involves a categorical variable with more than two groups, and then your dependent variable needs to be continuous. So for this analysis, my research question is going to be, is there a significant difference in students' GPA last semester according to class year? So as we know, class year, we can just click on here and check. Yep. 4 categories right here, so that's useful for our contrast. And then here's GPA. Here's GPA last semester, and it's a scaled continuous variable, so that'll work well for our dependent variable. Okay, so how do we run the test? We just go up here, analyze, compare means and proportions. We go down past all of our t-tests to one-way ANOVA. All right, so let me find here class year. That's going to go in what we call the factor, space on SPSS, the factor box. And then GPA last semester is our dependent variable. If you want, you can run a bunch of one-way ANOVAs about class year. We could put in all of our different continuous variables and look at that if that was our research question, of course. But right now, I'm going to make this simple and just use GPA last semester and class year study. Okay. There are a few things that I suggest you also tell SPSS to include in your output for your one-way ANOVA. First of all, click on here on your options. I like to ask SPSS for both to give me some descriptive statistics, because that just helps you to get a baseline idea of what groups are different and kind of like eyeballing your output. And then you also want to, or I strongly recommend, asking for what's called the homogeneity of variance test. It'll produce this thing called the Levine statistic. Remember, one of our assumptions of ANOVA and all of these types of tests is that our variances are homogeneous. And so we hope that we can not reject the null in this case. You'll hear a lot, and as I've already mentioned, ANOVA is a robust, quote unquote, test to a lot of the assumptions that we make, but still it's good to just at least check it out. So homogeneity of variance test, descriptives here. I'm cool with a p-value of 0.95, but you could change that to be, more rigorous or more, I guess, flexible if you wanted, but let's stick with 0.95. The other thing besides the options is we want to ask for a post hoc test. So as I mentioned already, the ANOVA omnibus test itself just indicates that there is some type of significant difference between at least one comparison of one of the two groups in our analysis. So if we get a significant result here, that just by itself won't tell us if the difference is maybe between first-year students and fourth-year students, or between second-year students and fourth-year students, etc. So we need to ask for a post hoc multiple comparison. So I'm not going to actually go into all of the details behind all of these post hoc comparisons because that's outside our scope. But my general recommendation between the two is, or between among all of these, is to use Tukey's post hoc procedure. And the reason why is that Tukey's test controls better for type 1 error. You can also consider using the Bonferroni test. Tukey and Bonferroni are both pretty conservative tests. So they have low chances of type 1 error. Usually Tukey is more powerful when you're looking and testing large numbers of means. So we have 4 groups here, right? So that's, larger numbers of means, 4 group means to compare. Bonferroni is sometimes better if you have smaller number of comparisons, so maybe just like 2 or 3. But generally, Tukey is accepted as having pretty strong power and not it's a pretty conservative test. So all this to say, I suggest also using the Tukey post hoc comparison. So let's check that. And then this is the test that I would like to run for my Oneway ANOVA. So I'm just going to hit OK, and we'll pull up our output. All right, so as I mentioned, I asked SPSS to give us the descriptives table. Again, this is just to eyeball what's going on here in our data set and see potentially which groups are different from one another. So we can see here that at least, descriptively on the mean, first-year students seem to have higher average GPAs than the rest of their colleagues who are more experienced. And then we can kind of also come over here, and the confidence intervals for the means can give us also some insight into maybe where significant differences exist. So more specifically, if the lower bound and upper bound confidence intervals of 2 groups don't overlap, then we can say they're probably different from each other at a 95% level of confidence. So what does that look like in practice? Okay, so for our first year students, their lower bound GPA is 3.01, upper 3.12. Oh, if we look down here, for all of these other groups, 2.87 to 3.0. Oh, at least this group here, second year students, their upper bound is less than the lower bound for the first year students. So probably that's where there's going to be a significant difference if our F-test indicates. And then 2, we could go, it looks like fourth year students, their upper bound is 3.04. So, and then for third year students, their upper bound is 3.02. So they might not be statistically different from our first year students or anybody else, because all of these confidence intervals for second, third, and fourth year students overlap. But let's get to the ANOVA F test and see what really is going on. Oh, right. Well, first, before we go on to our ANOVA table, remember I suggested checking the box in our sort of commands for the homogeneity of variance test. Again, one of the assumptions of ANOVA is that the variances are homogeneous. So in this case, we want our results to not be statistically significant. So as you can see here, our p-value is 0.49 if we were looking at a mean comparison or a median comparison. You can also do that. But usually, ANOVAs, we look at means often. But anyways, regardless, this is a good sign for us because it means that there are equal variances among our groups here. So we failed to reject the null. There are not significant differences in the variances between our groups here. So great, we have not violated the homogeneity of variance assumptions. Okay, now coming down here to our ANOVA results. Here is the basic output, and this tells us the global test for overall model significance. So from this, we can conclude that the means between groups are significantly different, but we can't make any statements about what means differ from this table. So since here, our F statistic is 3.5, and that corresponds to a significance value of a p-value of approximately 0.015. So p is less than 0.05, so we can conclude that the means between groups are significantly different at a 95% confidence level. However, as you know, we cannot make any statements about which means differ from the table. I don't know why I said that. Differ from one another between groups. So that's why I asked for that post hoc comparison. If I hadn't checked that post hoc comparison box, then we wouldn't know exactly where those means are different. But I did, so let's now look down there at the post hocs. Okay, here we go. What we really want to focus on is this mean difference column. So that essentially calculates the difference between each group's means, right? So here's for our first year student, this can be interpreted as the difference between the means of first year students' GPA and second year students' GPA. Then this row here, the difference between first year and third year students' means here. And then finally first and fourth year, and then you can, SPSS does the contrast for each level. So there's some redundancy here in the table. But this is where we want to look. And as you can see here, the SPSS shows you which differences are statistically significant by putting a star next to those that are. But then you can also, if it didn't do that, look over here at our significance column, right? And we see, for instance, the difference in means between first and second year students is statistically significant at a p-value of less than 0.05. The difference between first and third years, not statistically significant, marginally, but we didn't quite get there. And there's not a difference, statistically significant difference between any of the other contrasts, right? Our only star here is the difference between first and second, and then it's the same exact thing here, second and first, same difference. So we can conclude, again, that there is a statistically significant difference between first year student and second year students' GPAs at Walla University or wherever our population of interest is. And the difference is first year students have on average higher GPAs by about 0.13 points on their GPA scale. And that difference, again, is significance at the 0.05 level. So SPSS also gives some other output, and this can be helpful in different contexts, but the basic output that I use when I'm doing ANOVAs is really this, of course, first of all, the omnibus test, then or the test of homogeneity variances, then the omnibus test here, and then looking down here at the mean differences. And I'll mention, you might recall, even just looking at these descriptive data table, I figured out by looking at the 95% confidence interval for the mean, I had a pretty good idea that the only statistically significant contrast would be between first year and second year students. But in terms of reporting your results, you'll want to use what we see here in the post hoc, the Tukey post hoc, multiple comparisons after the omnibus test gives us the green light to go ahead with that. Okay, so just as importantly, we want to clearly and thoroughly explain in words to our audiences what our test results are. So here's how you would write it up according to APA. A one-way ANOVA revealed significant differences in average GPA according to class here. So you'd put in your F statistic here. So you want to put it in italics. Oops, the P should also be in italics. Sorry about that. For APA purposes. And then in parentheses here, you have your degrees of freedom, both within groups as well as between groups. That is displayed on your output for your omnibus test. And then you put in here the actual value of the F statistic. So the F statistic for degrees of freedom within groups, and then between groups, 3,972, and then our F statistic of 3.53. And then you also want to put the p-value for your omnibus test, right? So sorry, that should be in parentheses or in italics. And then you want to report your post hoc results. So to be very thorough about it, I would say a Tukey. So you want to say exactly which post hoc test you ran. So we ran Tukey in this case. A Tukey post hoc test indicated that first year students had significantly higher mean GPAs than second year students. And that was, as you'll recall, at a the p-value was, I think it was 0.01 something, but it was less than 0.05. Then on average, I would get into more detail to tell my readers exactly what that mean difference was. On average, while a first-year students' GPAs were 3.07 compared to 2.94 for second-year students. I got that information from my descriptives table, right? And we found that that was a significant difference. You could put in the mean difference too, but at least for myself as a reader, seems to be clearer to say that the first-year students' GPA was 3.07 compared to 2.94. That helps us kind of understand that difference even better, right? However, you would conclude by saying as well, there were no significant differences between any of the other class groups. So you don't really need to report those results in the text when there aren't significant differences. But of course, you would also include in your paper a table with the full ANOVA results, and you would put maybe those contrasts that weren't statistically significant even in there so that your readers would have a more comprehensive understanding of your findings. But in terms of in the text itself, unless you had a very precise research question that was like about fourth year students or something like that, typically you'd report in the text the results that were statistically significant in more detail than those that weren't. A final point I want to make is that there are lots of different types of ANOVAs. We're just covering sort of one of the most basic types for purposes of this class, but I want you to be aware that there are many other uses for ANOVA and slightly different approaches. So the types of ANOVAs, the different types of ANOVAs basically can be categorized in terms of whether or not your variables represent distinct groups of participants or the same participants. So the example we've shown you here is independent ANOVA, which means that your independent variables represent distinctive groups of participants. So, in this case, we did class year. Students cannot be first year students at the same time as being fourth year students, right? So they're independent groups. But you can also run ANOVAs, repeated measure ANOVAs on students who can potentially be in the same group. So maybe participating in various different types of training programs. So somebody, a university maybe offers ICT training, they offer, different software specific training. So the same participant could be, taking an ICT training as well as maybe an SPSS training, or maybe somebody has not taken any of those. So there could be sort of, overlap in terms of participation in certain types of experiences, and that would require repeated measures ANOVA. And then finally, a mixed ANOVA would be one where you're looking at variables that are both independent as well as repeated measures. So that's one way of describing your ANOVAs. And then also X-way, number of ways. So we learned here a one-way ANOVA because we just looked at one independent variable, which in this case was class year. But you can do a two-way ANOVA, you could do a three-way ANOVA, etc. So for example, it's easier to explain using real cases here. So what we did here was a one-way independent ANOVA. We had one independent variable, as I mentioned, measured using different participants, so class year. And then we looked at the impact on GPA, right? But the dependent variable is not doesn't matter in terms of the type of ANOVA. As long as it's continuous, you can look at multiple dependent variables or just one. The sort of language around ANOVA refers to the contrast and the comparisons you're looking at independent variable-wise. So let's say I wanted to do a two-way repeated measures ANOVA. So going up here again, helping us understand two-way, probably two independent variables. Yes, two independent variables, both measured on the same participants, right? So maybe we could look at change in digital literacy over time. So students sort of self-reported digital literacy over time. And we could look at how maybe that interacts with the types of training programs they participated in. So that would be two-way repeated measures ANOVA. A two-way mixed ANOVA would be if we looked at, again, X-way, so that's the number of independent variables. So again, two independent variables here. But one, we would be looking at, where different participants, so gender, you can only be one gender, at least for purposes of our analysis here. I'm not going to get into the geopolitics and sort of gender identity here. But anyways, and then our other independent variable would be measured using the same participants, right? So that would be the same students and their change in digital literacy over time. Then we could also, as I mentioned, you don't have to just do one or two independent variables. You could also maybe even do three independent variables, and that would be a three-way ANOVA. Maybe if we did a three-way independent or ANOVA looking at, I don't know, digital, what would our dependent variable be? Maybe digital literacy, and we're interested in seeing whether or not digital literacy is affected by class, year, gender, and ownership of a digital device. So that would be a three-way ANOVA. And again, all of these three variables here, class, year, gender, and owns a digital device, students could only be assigned to one of those categories, and that's why it's an independent ANOVA. So again, lots of different types of ANOVAs that you can run. The sort of foundational one is the one that we sort of learned about here, one-way independent ANOVA, but you can play around more in SPSS with all of these other different types as you start doing more sophisticated analyses. And these are especially, useful for experimental designs in quantitative research.